Okay, in this video we're going to talk about closure under vector addition. So this is one video that will lead up to the definition of a subspace of Rn. And a subspace of Rn is a very important type of subset of Rn, but the definition of a subspace is a bit complicated, and first we have to understand closure under vector addition. So let's talk about what that is. So if you have a non-empty subset, if you don't know what non-empty subset means, it just means it's not the empty set. Don't worry so much if you don't know about the empty set. It's like a set theory thing. The empty set is defined to be the set without any elements in it. So we're just talking about a subset of Rn that actually has elements in it, which is pretty much the only case that we're interested in. So a non-empty subset S of Rn is called closed under vector addition if, whenever V and W are vectors in S, the sum is also an element of S. So this is saying that whenever you have two vectors in S, and you add them, the result is also in S. Let's look at some examples. So let's say that you have R2, so n is 2, and let's say that S is the set consisting of vectors x and consisting of vectors xy such that x is greater than or equal to 0 and y is greater than or equal to 0. Well, what does that look like? So here's R2. The vectors where the first component is greater than or equal to 0, the second component is greater than or equal to 0. What does that look like? It looks like this set. It's all the vectors right in the first quadrant. Here's S, and it also contains the vectors along the axes because it's greater than or equal to 0. So that's your set S. It's all the vectors that start from the origin, and the tip of the arrow lies in the first quadrant. Now, is S closed under vector addition? Well, remember, when we're asking these questions, we want to translate it using the definition to a question, that we understand what it's asking. So when it's asking, is S closed under vector addition, it's saying, is it true that whenever you take two vectors in S and add them, the result is an S? Well, what do you think? The answer is yes. It's true that whenever you take two vectors that lie in the first quadrant and add them, you get something in the first quadrant, right? So S is closed under vector addition. Okay, let's write a proof of this. So because if you take two vectors in S, so let's say V is A1 plus A1, B1, and W is, maybe A1, A2, and B1, B2, right? If you take two arbitrary vectors in S, then, we know that A1 is greater than or equal to 0, A2 is greater than or equal to 0, B1 is greater than or equal to 0, B2 is greater than or equal to 0. So V plus W, well, that's going to be A1 plus B1, A2 plus B2. This is an S because A1 plus B1 is greater than or equal to 0, and a2 plus b2 is greater than or equal to 0. All right, let's look at another example. Again, in R2, let's say that S is the set of x and y such that x is less than 1. Okay, what does that look like? Let's draw a picture. So the first, so here's the x coordinate, the y coordinate. Here's x equals 1. And you want all x and y such that x is less than 1. So it's going to be all the vectors that start with an origin, and then the tip is in this set S. It is in this half plane to the left of x equals 1. Well, what do you think? Is it true that whenever you take two vectors here, you add them, you stay in the set? Well, the answer is no. This set is not closed under vector addition because, so to show that S is not closed under vector addition, you have to show that there exist two vectors in S such that when you add them, the sum is not in S. Now, can you come up with two vectors that will do that? Let's say you take, there's lots of different possibilities, but let's say you take 1/2, 1/2. So this is an S because the first coordinate is less than 1, right? And if you take 2/3, 0, that's also an S because the first coordinate is less than 1. But the sum, now do you see what's going to happen to the first coordinate? This plus this is going to be 7/6, 1/2. And this is not an S because the first coordinate, because 7/6 is actually greater than or equal to 1. So that's an example of a set that's not closed under vector addition. By the way, let's make sure we use the correct terminology. You say closed under vector addition. You don't say addition is closed. You don't say anything else. You can say closed under addition because, we understand that we're talking about addition of vectors. So closed under addition is okay. Closed under vector addition is kind of clearer in case it's ambiguous. But we definitely wouldn't say addition is closed, or we wouldn't say anything like that. All right, let's take a few more examples. So let's say that S is the set of x and y. Well, vectors x, y such that x plus y is 2. Is that closed under vector addition? So pause the video and think about it. Well, the answer is no, it is not closed under addition. And to justify this, we have to find two vectors in S whose sum is not in S. Well, we can take, say, 0, 2, and 2, 0. These are in S because x plus y is 2, but the sum is 2, 2, which is certainly not in S because 2 plus 2, just in case it's not obvious, because 2 plus 2 is not equal to 2. Now, what does this look like? It's all the vectors whose tip lies on this line, x plus y equals 2, and that's the line for 0, 2, and 2, 0. So what's going on is S consists of all these vectors like this. Right? That's what S is. And it's true that if you take two vectors, you can find two vectors that when you add them, the result is not an S. In fact, it's actually not possible to come up with two vectors in S whose sum is an S. Because if you have the first vector, the sum is 2, the sum of the components is 2, and then when you take your second vector, the sum of the components is 2. So when you add them, the sum of the components is actually 4. So it's actually really easy. I mean, any example that you come up with, the sum will not be an S. Okay. And by the way, going back to this example, right, we came up with two vectors that were in S whose sum was not an S. It's not true that every single time you have vectors in S, the sum is outside S. I mean, you can take, 0, 0 is an S, right? 1/2, 0 is an S, and when you add them, you get 1/2, 0. That's also an S. But closed under vector addition doesn't mean sometimes the sum of two vectors in S is an S. It's saying every single time. This is important. Every single time, whenever you have two vectors in S, the sum is also an S. Not sometimes, not, most of the time. It's every single time. And that is not the case in the second example. By the way, the two vectors you're adding could be the same. Okay, so when we're saying that whenever V and W are vectors in S, V plus W is also an S, it could be the case when we're coming up with counterexamples, it could be the case that V and W are the same, right? So if you have a subset and it contains a vector V, but then 2V is not an S, right? So let's say that V is an S, but V plus V is not an S, well then that set would not be closed under vector addition. Okay, so it's very important to keep in mind that this, we describe the set S as a line, as this line, but it is not closed under vector addition. That's important to keep in mind. What happens if we make the line go through the origin? So let's say that S is a set of xy such that x plus y is equal to 0. So this is a subset of R2. Is this closed under vector addition? Well, the answer is yes. So it looks like, so this is just y equals negative x. So it's going to be this line, right? It's all the vectors where the tail is at the origin and the tip is on the line. So this is your set S. Now notice that, as you can see from the picture, whenever you take two vectors in S, the sum will still stay on the line. So let's prove this algebraically. So this is in fact closed under vector addition. Okay, so the proof of this is, so we need to take two arbitrary vectors in S and show that the sum is in S. So suppose that you have two random vectors in S, V and W. Okay. Then by definition, because it's an S, we know that the sum of the components is 0. So then we can write V as A1, A2, where A1 plus A2 is 0. This is an equals. And W, the components of W, let's call them B1 and B2. And B1 and B2 equals 0. So therefore the sum, well, the sum is A1 plus B1, A2 plus B2. And we have that the sum is this an element of S? When you add the two components, do you get 0? Well, yes, right? This is an S because when you add two components, A1 plus B1 plus A2 plus B2, This is, okay, I guess we can show some steps. This is A1 plus A2 plus B1 plus B2. We know that since V is an S, A1 plus A2 is 0, and we know that B1 plus B2 is 0 because W is an S, 0 plus 0 is 0. And these are the scalars 0, just in case it wasn't clear. So therefore V plus W is in fact an S. And so S is closed under vector addition. So whenever you have a line that goes through the origin, that set is in fact closed under vector addition, but whenever it's not going through the origin, it will not be closed under vector addition. I mean, what was critical is the fact that 0 plus 0 is 0, right? I mean, this was used in the proof. But you know, if you have vectors where the sum of the components is where each component, the sum of the components is 2, then when you take two vectors and add them, then the sum of the components will be 4, right? So yeah, you won't stay in S. Okay, so those are some examples of closure under vector addition. And that's the first ingredient in the definition of a subspace. The second ingredient is closure under scalar multiplication. So we'll talk about that later. And then we'll talk about the definition of a subspace of Rn. Okay, thanks for watching.